Okay, in today's discussion, I want you to solve some problems.
Okay.
So I'll be here,
Okay.
and you can use the tablet and work out the details.
Okay.
And I have the graph of a function which I will define in this.
Okay.
So please use the pen drive and then
Okay.
see the graph.
Okay.
Okay. Shall we discuss our problems?
Yes, ma'am.
Okay. So try to discuss the continuity of the following function. Write down.
Yes, ma'am.
F is a function from R to R, and it is defined by f of x is equal to sine 1 by x for x not equal to 0.
Okay.
And it is equal to 0 for x is equal to 0. So you see the graph of the plot here.
Yeah.
So much fluctuating.
So I want you to discuss the continuity of this function.
Okay, ma'am. From the graph itself, it is also clear that the function is continuous at all x which is not equal to 0.
Correct.
Now, because the function 1 by x is continuous everywhere except 0,
Yes.
and sin x is continuous everywhere. So, by composition of two continuous function, I can say that it is continuous everywhere except 0.
Okay.
So, only the 0 point we have to carefully discuss.
Yes.
Yeah. So let me try for the continuity at x is equal to 0.
Yeah, see you.
So let me fix x naught is equal to 0 be fixed in the domain of f.
Right.
I need to look at all those x close to 0.
Right.
So I need to look at all those x such that modulus of x minus 0 is less than delta, that is minus delta less than x less than delta. So now given any epsilon greater than 0, to check the continuity, I need to check that for all x such that minus delta less than x less than delta,
Yes.
and for x not equal to 0, I need to check that modulus of f of x minus f of 0, which is equal to modulus of f of x minus 0, since f of 0 is 0. This is equal to modulus of f of x. I want this to be less than epsilon. Yeah.
That
So,
is, what is f of x?
yeah, that is my f of x is sine 1 by x. I want modulus of sine 1 by x less than epsilon whenever I have x lying between minus delta and delta.
Correct.
This is what we want.
Yeah.
Yes.
But the graph itself is showing that whatever small delta I choose here, I always have some point in that delta neighborhood where it takes the value 1 and minus 1.
Yeah.
Okay, what are those points?
Those points where it takes 1 will be, the points will be x is equal to 2n pi plus pi by 2. I will have sine of x is equal to 1, and for 2n pi minus pi by 2, I will have sine of that value to be minus 1.
Okay. How does that help?
Yeah. So let me conclude it. If x minus 0 is less than delta, I need to have f of x minus f of 0, that is sine 1 by x less than epsilon.
Yeah.
But I can find that this 2n pi plus pi by 2. So when 1 by x is this 2n pi plus pi by 2, then sine 1 by x is becoming 1, or when 2n pi minus pi by 2, it is becoming minus 1.
Yeah.
Now so I need this 1 by x, x in the small neighborhood of delta. So now if I take x as 1 by 2n pi plus pi by 2, and using the Archimedean property we can always find some n naught in natural number such that whenever n is greater equal n naught, I have 2n pi plus pi by 2, it should be greater than 1 by delta.
Right.
So 1 by 2n pi plus pi by 2, it should be less than delta.
Fine.
So this is in the delta neighborhood, and at this point when x is 1 by 2n pi plus pi by 2, f of x is 1.
Yeah.
So f of 1 by 2n pi plus pi by 2 is sine of 2n pi plus pi by 2.
Yeah.
This should be 1.
1.
Yeah.
So mod, if I put, it will be mod of this. So mod of 1. So this is equal 1. So but I needed this to be less than epsilon.
Right.
But if I choose now, say epsilon equal half, which is less than 1, then I have that this value is not less than epsilon. This is bigger than epsilon. So whatever delta I choose, there always exists such point in that delta neighborhood such that f of x minus f of 0 is bigger than epsilon. Any epsilon less than 1, say epsilon half, there does not exist such a delta. Hence we can conclude that the function is not continuous at 0.
Yes, you are correct.
So the function is not continuous at x is equal to 0.
Yeah.
Okay, fine. So, have you done sequences,
Yes, ma'am.
properties of sequences, convergence of a sequence in your undergraduate program?
Yes, ma'am.
Okay, in that case, the following result is going to be very useful in testing for continuity of a function f of x.
Okay.
The result states that if you want to test continuity of a function f at some point x naught in its domain, the result is as follows. A function is continuous at x naught if and only if for every sequence xn in the domain of f that converges to x naught, the sequence f of xn converges to f of x naught.
Okay.
So, in your example, if I have to use this property, right, then I should choose a sequence xn, isn't it?
Yes.
So, suppose I choose the sequence xn to be 2 by 4n plus 1 into pi. Then, what do you say about the limit of xn as n tends to infinity?
xn tends to 0.
Yeah, this
Okay.
should tend
So,
to 0.
what can you conclude about the sequence xn?
Xn is going to 0.
So, now consider f of xn.
So f of xn will be sine of, since xn is non-zero,
Yes.
so it will be following the sine 1 by x definition. So sine of 1 by this
4n
plus
plus
1
into pi by 2.
pi by 2. So it is nothing but sine of
2n pi plus pi by 2.
Right.
So it will be sine of 2 pi by 2, and that value will be 1.
1.
So, is it f of 0?
No.
This is not.
So?
This is constant sequence 1. This should converge to 1
So, it
itself.
is not equal to f of 0.
Yeah.
So, right. It is not equal to f of 0, which is
0.
c. So, what do you conclude from here?
Using this result, we can say that f is not continuous at x naught. Our x naught here is 0. So this criterion of continuity is useful to say that a function is not continuous at a particular point.
Okay, that's good. You understood the sequential approach of showing
Yes, ma'am.
whether a function is
Continuous.
continuous or not.
Yeah.
Is it clear?
Yeah.
Yes, ma'am.
That's fine. Okay, so let's now take another example.
Okay.
Right? So you now try the following problem.
So you should write.
Sushmita, will you
Yeah.
try? A function is defined on the whole of the real line
Okay.
as follows.
As
F of x is equal to 0 if x is not rational.
x is not rational.
and f of x is equal to 1 by q.
Okay.
If x is rational and x is equal to p by q in its lowest terms. Clear?
Yeah.
So, I want you to discuss the continuity of this function f
The,
at any x which is in the real numbers.
the definition itself is very weird. But one thing I can conclude surely that it is not continuous at any rational number.
How?
I have to use, because see, ma'am just now told that sequential criteria, right?
Yeah.
So we have to use that.
Okay, yeah.
Yes, use it.
So, so for example, say x is p by q. Oh, I should write x not as p by q, a rational number. So I want to conclude that this function is not continuous at this point. Now p by q in its lowest form, so f of x naught will be 1 by q.
Okay.
Okay. So now I construct a sequence xn which will converge to x naught, but so I mean that this xn sequence, it is in r minus q, means all the sequence of irrational number that is converging to x naught.
That is, xn's are all irrationals and
Yeah,
it converges
it
to
is
x naught.
converging to x naught.
Okay.
Because I can find such a sequence because irrational numbers is dense in real numbers.
Okay. Yeah.
How do you define that a subset D of the set of real numbers is dense in R?
I will define. So, a subset D of R is said to be dense if every x belongs to R can be expressed as a limit of
Okay.
a sequence of elements in D.
Fine.
Yeah.
So now, irrational number is dense in Q, so I can construct such a sequence which will converge to x naught. For this xn, what will be my f of xn? F of xn will be constant sequence 0, and this should converge to 0.
Yeah.
But what is my f of x naught? F of x naught is 1 by q, which is not equal to 0.
Yeah.
So f of xn is not converging to f of x naught.
Yeah.
But xn is converging to x naught.
Yeah.
Hence, this proves that the function is not continuous at x naught. So, since x naught is any arbitrary rational number, we can conclude that f is not continuous at rational numbers.
Yeah.
Yes, you have
Nice.
used the definite sequential approach and you have shown it. Okay, Sushmita, why don't you try the epsilon delta approach, because you said you have understood it clearly.
Yeah.
You solve any problem with epsilon delta approach.
Yeah.
Yes, right.
So let me try. Let x naught is equal to p by q be a rational number. In its lowest form. You have already proved that f is not continuous at the rational points using the sequence criterion. So now we have that f of p by q is equal to 1 by q. So I guess we need to find an epsilon which will depend only on this q, because the function value is 1 by q for every p by q. I think we should find an epsilon which does not depend on p, which will purely depend only on q. What do you think?
Yeah, I think that epsilon should be something which will be less than 1 by q. Maybe 1 by 2q.
Yeah, we will take 1 by 2q and check if this works.
So let us try with this 1 by 2q. Now for continuity, what we have to get? We have to get a delta such that whenever x minus x naught is less than delta, this should imply f of x minus f of x naught to be less than epsilon. which
What
is
is
in
your
this
x
case
naught?
1 by 2q.
What is
Now-
your x naught?
X naught is p by q here.
Yes.
So it is like I have to get f of x minus 1 by q to be less than 1 by 2q.
Okay, now I see the proof. I can
Yeah.
complete it now.
Okay.
So, what we can do is, we can always find an irrational number, an irrational xi close to x naught. So, such that mod xi minus x naught is less than delta. And now for this xi, f of xi minus f of x naught is equal to, since xi is an irrational, f of xi is 0 minus f of x naught is 1 by q. This is equal to 1 by q, but this is not less than 1 by 2q.
Yeah. So for epsilon equal 1 by 2q, whatever delta I choose, for any delta, I always have some x delta in this neighborhood, say x naught minus delta to x naught plus delta. In a delta neighborhood, I always have such a point x delta such that f of x delta minus f of x naught is bigger than epsilon.
Yeah.
So epsilon equal 1 by 2q. For this epsilon equal 1 by 2q, I don't have any delta which will work.
Yeah.
So it will prove that discontinuity at a rational points.
So the given function is discontinuous at all rational numbers.
Yeah.
Yes.
Okay. What about the continuity at irrational points?
That I think it will be very tricky.
Yeah.
We don't know how to start.
Okay. I'll give you a hint.
Okay.
Yes, ma'am.
You start with an irrational number. Okay. Take Sushmita. Take xi to be an irrational number.
So let xi be an irrational number.
Okay. And take epsilon to be greater than 0.
Okay.
Now consider a typical neighborhood of psi, and there are going to be rational numbers p by q in this neighborhood. So can you see some condition on the denominators q of such rational numbers which are in a typical neighborhood of this irrational number psi?
What do you mean by typical neighborhood?
I just mean an open interval around the point psi.
Okay.
Okay.
Alright. So for example, you can consider the open interval to be, say, psi minus 1 to psi plus 1.
Okay.
Okay.
So, and consider the rational numbers p by q in this open interval.
Okay.
And see what happens to modulus of f of psi minus f of p by q. Now, f psi is an irrational number.
Yeah.
So it will be
So
0.
f of psi is
0.
0 and f of p by q is 1 by q by definition of the function. So it is modulus of 1 by q. So the question now is, how many such rational numbers p by q are there in this neighborhood psi minus 1 to psi plus 1 with 1 by q greater than or equal to epsilon? Is the question clear?
Okay.
Yes. This means that q is less than or equal to 1 by epsilon. This, I think there should be only finitely many rational numbers satisfying this. Yeah.
So let us call them as P1 by Q1, P2 by Q2, up to say Pk by Qk. Let us, why don't we draw this? Let us draw in the line itself.
Okay.
Say this is my real number line, say this is 0, say this is my xi, and this is say typical neighborhood, delta neighborhood of xi, and I have this
I
point.
told you to take it to be psi minus 1 by psi plus 1.
Yeah.
Okay.
Those.
Xi minus 1 to xi plus 1.
Yes, sir.
Okay, and say this is my point P1 by Q1, P2 by Q2. Let me write 1. P2 by Q2 up to say these are the thing. Say this is pk by qk. So these are my rational numbers for which 1 by qj is greater than epsilon.
Yes, you almost solved the problem. So now look at the nearest P by Q, right?
Okay.
To the point side. I see that in your figure, P4 by Q4 is nearest to psi. Is that right?
Yeah.
Okay, so now continue. See whether you can proceed.
Yeah, I can complete the argument, I guess. Let me try. So, let us take modulus of xi minus the nearest point to xi, P4 by Q4 is equal to delta.
Okay.
So, in this neighborhood, for every rational number P by Q, we have modulus of f of
P by
xi minus f of P by Q is equal to 1 by Q, modulus of 1 by Q.
less than epsilon.
Yeah, less than epsilon. So now for any x in the neighborhood xi minus delta to xi plus delta, we have modulus of f of x minus f of xi is equal to either 0 if x is not a rational,
Yes.
or 1 by q if x is rational.
Fine.
This is anyway less than epsilon. So this proves that the function f is continuous at all the irrational points.
Yeah. Yes.
So, what is it that you have shown? You have shown this function that I have given you is continuous at all irrational numbers and is discontinuous at all rational numbers.
Yeah.
Isn't it?
Yes.
That's what you have shown.
Very interesting example. ma'am.
Yeah, yes, it is very interesting.
Yeah.
Of course. Okay, then what else do you want? Maybe let's do a different type of a problem. Namely, let us assume that we have a function which is continuous.
Okay.
So
And suppose say some condition is given on f. And using continuity of the function, we should be able to get some result. Let's try out something like that.
Okay.
okay.
Okay, so take this problem. I have a function f from R to R
Okay.
and it is a continuous function.
Oh, it is given continuous.
Yeah, f is given to be a continuous function.
Okay.
Alright. And this function f satisfies the following condition. Write down the condition. F of x plus 1 by n is equal to f of x for any rational number x and any positive integer n. Alright. Is the condition clear?
Yes.
F is such that f of x plus 1 by n is f of x for any rational x and positive integer n. What is my question, or what is it that I want? I want you to find the value of f at square root of 2017. Is it clear?
Oh, yeah. So we are given a continuous function and the function, there is some condition on the function at the rational points.
Correct?
And we are asked to find the value of the function at an irrational number.
Exactly.
Oh.
So from the given condition, what I immediately can say that f of x plus 2 by n,
Yes.
it will be f of x plus 1 by n plus 1 by n.
Fine.
So this will be f of x plus 1 by n,
Correct.
and that will be f of x for any rational number x and for any integer n.
Yes.
Okay, so here you are considering this as the x and then you are applying the condition. Okay. So in this case, by induction, we can tell that f of x plus m by n is equal to f of x for any rational x and for any positive integers m and n.
Yes.
Yes, you are on the right track. Continue.
Now considering x to be 0, we can say that f of m by n will be f of 0
Yeah.
for any positive number
Yes.
m by n. So for all positive rational number we have f of that positive rational number m by n, I have f of m by n to be f of 0.
Yes.
So now we have to do for
The
negative numbers.
Yeah.
Okay. So now if I take a negative number, say x equal minus m by n, then x plus m by n will be 0.
Yeah.
Now f of x plus m by n, it will be f of 0, but f of x plus m by n, it should be f of x.
Yeah.
That means f of minus m by n. So I can say that for any negative rational number also, say minus m by n form, it is equal to f of 0.
Yeah. So for any rational number, f of p by q is equal to f of 0. But we have to find the value at an irrational point, right?
Now I will use that earlier argument that I used for the last problem. I will construct a sequence of rational number in this case that will converge to this irrational number.
And that is where we use the hypothesis that f is continuous.
Yes, absolutely.
Okay.
So I have that f of x equal f of 0 for any x in rational, right?
Yeah.
And I construct a sequence in rational number such that xn is converging to root 2017.
So you are denoting a set of rational numbers by q now.
Yeah.
Yeah.
Okay. All right.
Okay. Then since f is continuous, so f of xn should converge to f of root 2017.
Yeah.
But f of xn is the constant sequence f of 0.
Yeah.
So f of root 2017 will be f of 0.
Oh, okay. So basically the function turns out to be a constant function. The constant value is equal to f of 0.
Yeah.
F of 0.
Yeah.
Yes, yes, yes.
So is there any speciality about 2017?
No, ma'am. For any irrational number, we can construct the same way rational sequence. And since on the rational it is constant f of 0, so for any irrational number also it will be that constant f of 0.
Okay.
So actually the function is constant on the whole real number.
Okay. Fine. That's good. That completes your discussion on this problem.
Yes.
Where you were given that a function is a continuous one and a condition on that function at some rational number helped you to evaluate the function at any irrational number. Isn't it? That's good. So what is the message that you get from this problem?
From this problem, I observe that a continuous function is completely determined by its values on the rational points.
Okay, that's fine. So in other words, if you have two functions f and g from R to R, and if they agree on the set of rational numbers, then they agree everywhere.
Yeah.
Yes,
Is that right?
Yeah. So what about what if they agree on irrational numbers?
You have to tell me.
Yeah, I think that they should agree everywhere because irrational number is also dense.
Oh,
so
yeah.
Basically I think that if continuous function, if they agree on a dense subset, then they will agree everywhere.
Okay, yeah. Both the rationals and irrationals are dense in R. So, yeah. So they will agree everywhere. Okay.
It's clear.
Yeah.
Yes, ma'am.
So by today's discussion, I was able to improve on problem solving skills and I could see the subtleties in all the problems.
Yes. So we have actually considered 3 problems.
Yeah.
And did you enjoy, Kuntal?
Yes, ma'am. I enjoyed very much. Now I can say that I am also developing some problem solving skills.
Yeah. So what is it that you did when I asked you to solve a problem? You made some observations
Yeah.
about the information that was given in the particular problem, and then once you had those observations, you started asking some relevant questions one by one, and one after the other.
Yeah.
And then these questions helped you to go in the right track.
Yes,
And finally you hit at the solution of the problem, isn't it?
Yeah.
So this is how you should try to develop your problem solving skills. So given any problem, you shouldn't be afraid at all. Make some observations, look at it and see what all things that you can get from the given problem. That's nice. I mean, you did try those problems and you were able to come out with proper answers and then proper questions. And yes, it was nice.
So can we discuss some more properties, ma'am?
Oh, now it is time. We have a seminar in our department.
Yeah.
Let's go for the seminar. We will continue this discussion tomorrow.
Okay.